Hi, I'm James, and welcome to Spring 2016 Midterm 1 walkthrough. I highly recommend, if you haven't done this midterm already, to take it either timed or to work through the problems yourself before watching this video. And each question will be linked in the description below. So let's get started. What would Python print? It's key to note that a lot of these questions might not even deal with the code that's written there. So these are sort of like free points if you understand the rules for Python. Okay, so for example, and. So and short circuits on the first false value, and it returns the last value if all values are true. So 3 is a true value. So we move on to ABS. ABS is actually a function, and this is a true value as well, because everything that's not none or 0 or an empty list or whatnot is true. So it'll return the last value and return ABS of 1, which is 1. Okay, print 3. Remember, we evaluate left to right. So print 3 is going to print. And then this actually returns none. Remember that print is a non-pure function. So it actually returns none, but does a side effect of printing 3. And none evaluates to false. So we go on to 1 divided by 0, 1 divided by 0 errors. Okay, print. Print is a function. Notice how this is different than a function call, which would have parentheses. And if you print this, type this in the interpreter, it'll say like, function, brackets, whatever, print. Okay, so list 1, 2, 3, if y divided floor div y plus 1, else 4, 5, 1. So y is over here. We plug in 7 and 8. Floor div, remember, is going to truncate the decimal. And so what will happen is this is not even 1 yet. So it'll truncate all the rest of the decimal and leave you with 0. Which is a false value. So how one-line if statements work, if you aren't familiar, this is our condition. So if our condition is true, it will return this value, else it'll return this value. And so what happens is it'll return this value. We get the first index of that, which is 5. Okay, W of 5. This is a little tricky because notice how we have 2 definitions of C. But remember your environment diagram rules where you sort of go, top to bottom, and you follow indentation, and you should be good. So first, let's just sort of read the code. So we have a B function that will return a lambda. We have a C function that will return 3. We have a W that we need to evaluate to get our W here, and we have another C function. So let's evaluate our W function. So let's look at operator operands. The operator is our B here. The operand is our C here, because this W doesn't have access to this C yet. So we actually pass in this C into our function as x, and then we just return this lambda, right? We don't go into the lambda. If you return a function, this is like so this is sort of like a higher order function. We don't actually return that. We don't actually call it yet until we have something like this. So W actually evaluates to this lambda. So we can actually just draw an arrow to this lambda. Now we call it on 5. So we write 5 right here, and then we do x of y, which is 5. And x, as I just have an arrow, is actually this C right here. So this is like saying C of 5, and it'll actually return 3. The trick part of this question is we're trying to trick you with this C definition down here, but it actually doesn't do anything because this C got passed into this function, and we return that higher order function. All right, let's do part B. Let's look at print, operator operands. We go left to right, so let's evaluate this first. I'm going to make a little mini environment diagram to help myself out. Parent equals global, so we called the function D. We set S to a list 1, 2, 3. I'm not going to draw the boxes, but you should draw boxes around those. F points to a function F. Parent equals F1, so that's that line right here. Now we go to the if-else statement. If the len of our list is 0, it's not. So let's go to our else statement. Remember, or short circuits. So if F1 were to return true, then our entire thing would turn true. But that's going to be key to note later on. So F1, let's see if F1 returns true. F1, is K less than len S? That is true. And remember, everything has to evaluate to true in order for it to be true. So we have to keep going left and right. So this value is true, but let's evaluate this. Well, left to right. Is s of 1 equal to s of 0? That's not true. Or, so this is not true. Or f of k plus 1. So k is 1. Now let's do a function call to k is 2. 2 is less than the len, and is s of 2, 0, 1, 2, equal to s of 0. That's not true as well. So let's do f of 3. f of 3, 3 is not less than the len, so this will return false. So this whole thing will return f. So let's evaluate d of s of 1 colon. So let's list splice. Remember, this will now make a list with 2 and 3. We'll pass that into our d here. And then, we can sort of see a pattern, because this is not going to be true. But when we do f of 1, well, f of 1 is going to be false as well, because notice how there are no repeated digits in our list. So this right here will never evaluate to true. So we know that this will it'll keep recursively calling over and over again until we actually hit the base case, because notice how it'll keep list splicing and calling d again and again and again until we hit the base case, and that'll actually return false. It's key to sort of notice these patterns when you're working through these problems that have a lot of recursive calls. So, okay, now let's do our d call for s points to 0, 1, 2, 1, 0. Notice how there are repeated digits. Let's work through the code. If len s is 0, it's not, else return f of 1. So let's do f of 1 for our call here. K is, there's a lot of, hopefully you can still read that. K is, so 1 is less than len of s. And then s of 1 is not equal to s of 0. But then we do f of k plus 1. So this will do f of k 2. 2 is len s, and but s of 2 is not equal to s of 0. So then we do f of 3. That's also not equal to the values are not equal. But when we do f of k of 4, so let's work through f of 4. 4 is less than the len, because our len is 5, and s of 4 right here is equal to s of 0. So this will actually short circuit. We won't do any more recursive calls. It'll return true here. It'll return true this f of 1 call here. And it'll print out true. All right, so environment diagrams. Let's start with the global frame. Y is 3. They already did it out for us, and then we will have to do this v. So let's evaluate the right-hand side first. Remember, evaluate operator operands. So we actually want to evaluate this first and not do that function call yet. So that's a function call. Our function is out. Our parent is global, as we see here. We have to first bind the formal parameters, so h and m. So this is none, and this is 1. Now we can work through the indentation here. So this is sort of our F1 code. Y is 5 times m. That's 5. Inner now points to a function inner. Parent equals F1. If m equals 0, m is not equal to 0. So let's do return out inner m minus 1. So out parent equals global as well. Formal parameters h and m. H is now the function inner. Oh wait, oops. Draw an arrow to function inner. M now is m minus 1, so 0. So let's now run through the code. Y is 5 times m, which is 0. Def inner. Notice how we actually create another inner. Notice how we actually create another function inner. We don't point an arrow to this inner because every time we saw that def statement, we actually have to create another function. And we're in the F2 frame, so this inner actually parent is F2. M equals 0, so m is equal to 0. So now we actually return h. So h is this function. Okay, so that means that this out right here returns this function. Now we evaluate it with one more parentheses. So we're going to actually be calling this inner function parent equals f1. Now we run through. It takes no arguments, and it returns y. So f1, let's look at, remember variable lookup, you look up the parents. Parent equals f1. Let's look up to f1. Y equals 5. Return 5. Now we set v equal to 5. All right, environment diagram part 2, def lazy. So we worked down the global frame. They already did the lazy call for us. And, you know, when you have something big like that, remember you do operator than operands. So in our case, our operator is lazy for first. Note that all this is, you wouldn't put this in your environment diagram. But lazy for, so we evaluate that because that's our operator. So we actually create a lazy, this is a function call, so you create a new frame, parent equals global, bind the formal parameters, n is 4, return now lambda k, n if whatever. All we need to note is that this is returning a lambda function, where it's nice to write the line number just in case there are multiple lambda functions, and this is the parent equals f1. Oh, and it's nice to write what arguments it takes in. So yeah, so this evaluates now to this lambda function. So we can cross out this. This is now this lambda function right here. And then we call it with 1. So this is actually now lambda, parent equals f1. N, oh wait, formal parameters, sorry, this is k now, because our function takes in k. K is 1. And then now we can actually run through this code. So we return n if k equals 0, else lazy n plus 1. So k is not equal to 0. We create another function call to lazy, n plus 1. So parent is now still global because our lazy function is in the global frame. N plus 1. So notice how we were in this call. Initially, we called the lazy call. And there's no n in this frame. So we actually look up to here. There's an n here. N is 4. We add 1 to there, so now n is 5. And then actually lazy is going to return a lambda function. Lambda. Notice how we don't point to this lambda function because actually every single time, remember, we're returning a new lambda, and this is actually a new frame. So this is still line 2, but the parent is f3 now because we returned it in the f3 frame. And so the whole point of that was to evaluate what this lambda would return, which is this lambda. Because this lazy right here returned a lambda function. So notice how if one line if else statements, we evaluate that, and then we actually return this. So that gets evaluated. So now this whole lazy for 1 evaluated to this lambda, and then we call it with a 0. Whoops, I crossed it out. So lambda, parent equals f3. Now we, k is, we bind the formal parameters. K is 0. If k is 0, return n. So notice how the condition is true. We return n. We look up the parents, f3. There is an n here. So we actually return 5. And then now we go up here. We say v equals 5. All right, so the extra credit point was whoever said this quote was this guy named Wolfgang Goethe. Only like 5 out of 800 people got that correct, so it doesn't matter. So let's do the code writing questions. These were really particularly difficult, but I think if you went through and really understood the question and then used the hints we gave you, it's not too bad. So we really want to understand what the question is asking before even attempting it. And so this was a very confusing question, but if we read through their example right here, L equals 314502, it has a cycle because basically the value, we basically take the value and then go to the index of that value. So, and then keep going. And if we ever get back to the beginning, that's a cycle. So their example is we start at index 0. We take L of 0 equals 3. 3, yeah. And then L of 3 equals 0, 1, 2, 3 equals 5. L of 5 equals 2, L of 2 equals 4, L of 4 equals 0, and L of 0 equals 3. Notice how we started back at the beginning again. So this is a cycle of length 5 because we went 1, 2, 3, 4, 5, and then we actually got back to a 0, which is the index that we started with. Notice how L of 1 equals 1, L of 1 equals 1, L of 1. This is not a cycle of length 2 because we don't actually allow repeated numbers in our cycle. So this would actually, I think, be a length of 1, but not of 2. And this is actually important to note when we go through our while loop. Okay, so let's read through. Def has cycle. True if and only if L has a cycle of length k greater than or equal to 1. Assume L1 is greater than or equal to 0 and less than ln, or len L, for I between 0 and len L. So that might seem a little confusing, but all this is saying is that for every index, or for every value, for every index, the value at that index is going to be between 0 and the len L. This will make it easier just in case we index out of bounds. We don't have to account for that. So let's walk through the code. Notice how they defined a helper function for us. L has a cycle of length k starting at s. So this is actually key because in the code down here, even if you didn't get any of this code here, you could actually still get some points just by using the English interpretation of this question, of this helper function. So this is saying L has a cycle of length k starting at s. This is looping through all the indexes. So what if we were to check, how can we check if a list has a cycle? Well, we could go through every single index and check if there's a cycle at that index. And that's exactly what we're going to do. Cycle at index j. And we could do actually equals true, because notice how this is going to be turning true or false. True or false. So cycle at j equals true. And we actually don't even need the equals true, but sometimes that's easier to understand. Return true, because that means there is a cycle. Else we'll actually return false. Because if we've gotten through every index and there isn't a cycle at any of those indexes, then we actually want to return false. So let's go into our helper function and start implementing the code. So let's actually make a variable p to actually start at the, brackets, to be the value at the L of s. To be the value at the index s. And we'll need that later on. And then let's look at sort of n plus 1, there's a while loop. So n is going to be a counter of some sort. Well, the only thing we need to count is k, right? Because L has a cycle of length k. Well, if we start n at 1, and then we increment n, and then once n equals k, then we know that we have some sort of path of length k, and then we actually have to check if that sort of path, whatever, like sequence of numbers is a cycle or not. And so we basically want our while loop to go until n equals k. So how to do that is we say n minus, while n is less than k, we'll keep incrementing n, and then once hit, so then basically this return statement is going to be when n equals k. All right, so then let's look at our if statement. Basically, we want to, so this is going back to what we were talking about earlier, how we want to actually return false if we ever get to the beginning of the list, but we're still not at n equals k. So something like this, where we got to the beginning of, not the beginning of the list, rather the index of s, and so we got to s equals 1, but we weren't even at n equals k yet, where k is 2. And so if basically the value, which is our p, is equal to s, we actually want to return false. So if the value, in our case 1, is equal to the index we started at, which was, the value here is equal to the index here, if that happened too soon, then we know that we've hit a cycle that's not at length k. It's actually less than length k. Okay, so now this line right here is going to be, we're going to have to reassign p to be the next value of, basically we'll take, so notice how we, first p started as 3, and then s started as 0, so this is s, this is p, and then we actually want to reset p to now be the value at L of p. So L of 3 is 5, so now p will be 5, and then we'll say p is now equal to L of 5, which is now 2, and that's sort of how we'll keep incrementing. And if at any time we hit somewhere that goes back to the beginning, then we know that we want to break out. Okay, so now how do we know that? So we filled out the while loop, but then at that return statement, how do we know we actually found a cycle or not? All we found is a sequence of numbers of jumping through indexes. How do we know that it's a sequence or not? And so we actually want to check if p is equal to s. Because if p is equal to s, that means we've made it all the way around. That the value we got here, right here, the value 0, is actually the 0 that we started with. And if it's not, then it'll return false. And notice how this is a nice, succinct way of writing a sort of if p equals s, return true, else return false, because if this is false, it'll evaluate to false and will return false. So that's that question. All right, another pretty difficult code writing question, but we really want to understand what the question is saying, understand the doc test, which in this case is a little chart, and then really use the pseudocode they gave us. So let's start looking at the doc test. So we want to multiply. We want to find every possible combination of multiplying two sequences at a time, and basically we can count the number of parentheses we can put into it to indicate, multiplying them two at a time. So let's look at, first we pass in a. Well, obviously there's only one way that we can multiply it because you just do a. Okay, ab, there's only one way, there's only ab. But then abc, notice how we could first multiply the b and c first, and then multiply it with the a, or we could multiply the a and b first, and then multiply it with the c. And then, a, b, c, d, we could first multiply the CD, then the B times that product, then the A, or we could multiply the BC first, then the D, then the A. And notice how it's almost like breaking up into smaller portions, right? Like this call right here is like a product of 3, right? Just that inner part. And then actually this is also a product of 3. And then this is just a product of 2 and a product of 2. And then that, just making sure. And also notice how all the A's, like this is grouped by, first all the A's are taken out first, and then we do a bunch of stuff with that. And then we take out the AB, and then we take out a length 3, and then we take out a length 4, sub grouping. And so, notice how we take out a 1, then a 2, then a 3, then a 4. That'll become pretty important. So hopefully you understand the question. Let's walk through the code. If n equals 1, so I assume n is the number of items that we're multiplying, return, well, they gave us the answer right there. We want to return 1. That's our base case. Okay, so we have a counter right here. We want to, I is going to be some sort of, notice how I actually wrote out this sort of counting, 1, 2, 3, 4. So I is going to be in charge of groupings by subgroupings. So first we'll group by 1s, then 2, then 3, then 4. So we actually want to start at 1. And which means that how can we keep track of the total number of count that we've done? We can't use I because I is going to be going 1, 2, 3, 4. So we actually have to introduce another variable, total, where we actually start total at 0, and then we'll add to total, and then we'll actually return total. This is sort of a classic. We have an index we're using to loop through something. We want to add up the sum. We have to add it to total, and we want to return total. Okay, while I is less than n, because basically, notice how we go 1, 2, 3, 4. We can't, obviously, if we had something like equals n over here, if we had it equals right here, that would actually go until, and it would still execute I equals n. And obviously, if we like we're using recursion somehow, you can't recurse with count groupings of n over and over again. It'll go forever. So we really want to start with groupings of 1, then 2, then 3, then 4. And this right here is actually a pretty good example of how we can do that. So we first want to add something to total, plus equals. And then this is the really hard part of the question. So we want to first group, actually not underline, we want to first group I subgroups, and then we want to group n minus I. Notice how in this example here, we pulled out the A, and then we actually had a subgroup of 4. Here we had pulled out the 2, AB, and then had a subgroup of 3. And we actually want to find all number of distinct parentheses possible in our subgroup. So that's taking this whole leap of faith. How we first want to, we first want to count the groupings of I items, and then we want to also count the groupings, count G, of n minus I. And this is taking the leap of faith. We'll sort the first i's, and then we'll sort the last n minus i's, and then we actually need to multiply them together because we want to find every possible combination of grouping the first I and then times grouping the second I. And this is actually can be seen a little bit more easier with n equals 6, with A, B, C, D, E, F. We want to group all possible combinations of parentheses between here, A, B, and then we also want to group it like this, and like pretend we're on I equals 3 call right here. We actually want to pick every possible combination of grouping the first 3 with the last 3. And we have to multiply them because there could be, like, basically we want to list out, A, B, C. This could go together with not only D, E, F, but it could also go together with D, E, F like that. And so just only one grouping of the first group can go with multiple of the second, and so we want to multiply. Sorry if that wasn't the most clear explanation, but I think really drawing out, separating. Notice how there's a pattern of how they grouped the A's. They had 1 group, then 2 group, then 3 group, then 4 group, and you have, I starting at 1, and then n minus I would be the last group, and we can't add them together because it's sort of doing what I was talking about here. You first group the first part, and then for every single grouping of that part, you need to group the second part. Yeah. All right, so let's start with the amazing problem. This was also pretty difficult, but so in lecture, did some problems finding through a maze, some booleans, yada yada yada, different representation. So we really want to understand the problem. Basically, we'll represented by functions. A maze function, say m, in this formulation describes the state of the maze from the point of view of a maze runner. M accepts a single direction, which describes the action. So then m returns a maze function that represents the state of the runner after taking the indicated step. It accepts a direction, so our maze function is going to accept a direction, and then return one of 3 things. It'll either return exit if we've reached the exit. It'll return dead end if we can't move anywhere. And basically, conceptually, if we haven't hit a dead end or we haven't hit an exit, then we actually want to check if wherever we're going is open, and then keep going. And so this seems like recursion because notice how we have to check every possibility of going south or west. Actually, I think that's for part B, but for part A, they simplify it. So all we have to do is just check the square in a certain direction, and then if that returns, if that's whatever a dead end, then we can't go. We'll return dead end. And if it's the exit, we'll return the exit. Let's walk through. Define a function predmaze that returns a maze function as described above. If m equals predmaze x, y, p, e, then m returns the runner in the maze, which the runner's at coordinate x, y. The squares are unblocked, so there are some a values that are unblocked, and so the square at a b is open. So if we do p, that's saying it's open. If and only if p is open. For example, suppose that q is a function such that QAB is true on all the white squares in the following grid, where just to be different, the lower square representation, or lower left square represents -5, -5. So we create a pred maze starting at 0 and 1. So 0 and 1, so we're right here. And then m1 equals mo of west. So we actually go west. So this is saying we're going to go west 1. So we're going to go west this way. So now we're at here. And then we actually call it west again. And actually the dead end here. And then we actually try to go south. So we go south. M1 south. Yeah, so that will return a function because, wait, will that return a function? M1 south. That should return, yeah. So if we can go to the next space, it should actually return a function that we then actually have to call again, just like what happened here. Yeah, my bad. So m1 equals mo of west. So we actually went west, so that was good. So then we actually return a function that we can then keep calling and calling and calling until we hit the exit. So m1 equals mo of west, we called that, we returned a function that we then called again, that got dead end. But we called it with south, and we actually could go south, so we actually have to return another function. So let's create m2 equals -3 and 1, we're there. And then actually we move west here, we're at the exit. Cool. So let's fill in the pred maze. Returns a maze in which the runner is at x0. Every square AB, where AB, so AB less than equal exit is an exit. That's key. And then otherwise, a square is open if open AB. It is assumed that the spot we're already on is not blocked, is open. So, okay. Maze, I believe it said earlier that our function should take in a direction. So our function is going to take in a direction. And actually, notice how dir equals south. So this would error if we didn't call our variable dir. What this is doing is this is a simultaneous assignment, which is basically going to evaluate if we're going south, we want to decrement our y value. Else, we want to decrement our x value. Does that make sense? On the graph, if we're going south, we want to decrement our y value. If we're going west, we want to decrement our x value. And you can't go southwest, so we can only do one. So yeah, we pass in south, we will decrement, remember one-line if-else statements, the condition is here, it will return this, and simultaneous assignment is cool because then we could say something like, 5, 6. What will happen is actually it'll assign each value to the values in the tuple. Cool. So what's the first thing we want to check? Well, the bullet point said we want to check about an exit. So if our a value, we're a and b here, so actually we want to use x value. If x is less than or equal to exit, actually not capital, exit, then we actually want to return, what do we want to return? Exit, I think? Exit. Oh no. We want to return exit. Else, now we want to check, so we could either check if it's blocked, then we return dead end, and then we keep recursing. But in our case, we actually want to do the opposite, because there's no way to check if a square is blocked or not, but we have a way to check if it's open. So we actually want to check if x, y is open, then we actually want to recurse. So we want to call pred maze with x, y open exit. And the reason why we want to call pred maze instead of maze is because notice how our maze is implemented, we want to return functions if we go to the right place. So in this case, pred maze is going to return a function. Else, we want to return dead end because this implies that we're not at the, this implies if it's not open, then we hit somewhere that's blocked, and we want to return dead end. All right, so this is part B, where we're actually going to print out the path that we can take to get to the exit. So let's walk through the doc tests. M equals -1, 1. That means we start at -1, 1. And then we want to print out, so we're right here, we want to print out, the path. So we go south, then west, then south, then west one more time. So if we go down here, it should print south, then west, then south, then west, then west. And if we're at a location that we can't get to the exit from, then we want to return none. And with that, they actually sort of did that for us. Okay, so we're going to be looping through either two directions. We can either go south or west. And we're probably going to have to use recursion just because notice how, we're going south or west, and we want to try every possibility of going south and west from those locations, and from those locations. So this is a common sort of recursion problem where if one of the locations leads to a path that is not none, then we know that we can add our direction to that. And we'll see that. So next to me, that seems like that'll be the next location we're going to. And how do we do that? We actually call M of dir, because M of dir will either return dead end, exit, or a function. And this function means that we're going in a location that we can go in. That's not a dead end, and that's not the exit. Okay, so we have to check if next is equal to exit. That means that we've finished. We can stop recursion. We can stop everything. This is like our base case, I guess. We return the direction, and then I think we actually have to add a space. A space to it. I don't know. They have that. All right. Now, how do we want to recurse if we hit a dead end? No, we don't want to recurse if we hit a dead end. So we want to only recurse, only do anything more if next is not equal to dead end. Okay, so then rest of path, that indicates, okay, so pretend that we went this direction. What will our path out, will that return, like we take the leap of faith. So for example, let's just say we took the south. We went south. That's what is implied by the next returning a function. Well, will going south return a list, a path out? And yeah, this is really tricky. Will that actually return a list? And so we want to take the leap of faith. Rest of path will be the path starting from the location that we went to. So path out of next. And notice how next is a function. M takes out a function, so it works out perfectly. If rest of path, basically, notice how if it isn't none, then we know that it must be a path. Because path out will either return a path or none. So if it's not none, then it obviously must be a path. So we can actually say if rest of path, and then we don't even have to say not equals none, because just evaluating it with the colon will actually return none or true. And so this will return true if path. Because, a list, or not a list, rather, a string, like a string like south or something, that's equal to true. Return, so now we actually want to add our direction to the front of the path, plus a space, plus rest of path. Does that make sense? So we basically, we first get the next location, we check if it's an exit. If it is an exit, then we know we can stop our recursion right here. If it's not equal to a dead end, then we know it must be a space that we can walk to. So we walk to that next space. We check if there's a path there. So we take the leap of faith. If it's none, then we can keep going. Then we'll continue to the next direction. But if it is true, then we want to add the direction to the front of that path. And then notice how if at any point we loop through both directions and none of this gets executed, or actually rather none of these if statements right here get executed, then we'll return none, which is what we want to do, which is something like that, what will happen there. So that was the Spring 2016 walkthrough, Midterm 1 walkthrough. Please post a follow-up if you have any questions or if something is inconsistent with the solution or with my walkthrough. Cool. Thanks for watching.